Hello all. Welcome to this class. So today we'll start. We'll continue from where we left last time.
Hello, good morning, sir. Hello.
Yes, sir.
Sir, am I audible, sir?
Pandey sir, we can hear you.
Sir,
Uh,
can you unmute your mic?
so actually, I wanted to make one request, sir. Hello.
I think professor is not audible, so that's an issue. Pandeyji, let's wait for him to solve it.
Am I audible now?
Yes, sir. Yes, sir. Yes, sir. I can hear you, sir.
Yes,
Okay.
sir.
Yes, sir. Yes,
Thank
sir.
you. Thank you. Okay. I think we can just hold on. I will just record the class again. It's recording now. It's recording. Okay. Let me just present my screen.
Radhakrishnan, sir, I want to make one request.
Yes, sir. Please.
Sir, that regarding the MATLAB,
Yes, sir. Yes, sir.
actually, most of the people in DOT will face the problem in the syntax and other parts of the MATLAB
Yes, sir.
writing.
Yes, sir.
So what I request you that for the most of that the duty officers, the people
Uh,
who won't be able to write the syntax and other parts, so
uh,
we can just for the homework part we can write the logic for that.
yes,
That
sir.
will be submitted, so it will be better because while going into that matter part of that, how to use the syntax and other parts, this will go lead me to some another word.
Okay, so what I will do is I will frame the question in such a way that you write both the logic and people who can do the MATLAB assignment, I encourage them to do. So
Yes,
this
yes,
week,
yes.
so what is going to happen is today MathWorks guys have promised me to come with a detailed set of instructions to install the MATLAB. Okay, I'm going to send. They said by today 12 o'clock or so they'll send it to me. Once they send it to me, I will send it to you with a detailed set of instructions. Okay,
Okay,
and this
okay.
week I will also ask the TAs if those who are interested in learning the MATLAB syntax. It should. I mean, so there's some small learning curve for it. It shouldn't take too much time. Those of you who are interested, I'll ask them to take one additional class sometime and start from the basics. Okay, whoever is interested can join that class because it's good to learn MATLAB. MATLAB if you want to learn 5G because it's easy.
I think there are some lectures on NPTEL also by IIT Madras on MATLAB. If anyone
Yeah.
interested, they can look at that also.
Ashok sir, can you just post those links in the Google Classroom?
Sure, sure.
Okay. Okay. Thanks. Okay. So let me just share my screen and we'll start. Sorry.
Sir, excuse me, sir.
Ashwati, tell.
Sir, there is a request in the chat asking if this Saturday's class can be moved back to
No, I
Thursday.
will. I will talk to. I will talk to him, and I will ask him if he can. This Saturday class will be more. I mean, a little bit. It will be recorded. He can use that lecture notes to
Yeah,
finish
sure,
up.
sir.
It's easier that
Okay.
way. Okay.
Okay, sir. Okay, sir. Thank you.
Am I recording? Yes. Okay. So last class, this is the point at which we left. So I'm going. So this is what we called as zero forcing. Okay. This is what we called as zero forcing. Okay. So let us not worry about the SNRs right now because that's a little bit more complicated. I don't want to get into that right now.
So what do you mean by the zero forcing over here?
So zero forcing means
what?
that's what I'm trying. So this is your channel. So this is your channel. Okay, this is the channel 0.5 into x of n. X of n 0.5 is the channel. So what you're doing, you are actually inverting the channel. You're inverting the channel by dividing by 0.5. Okay, such kind of inversion, direct inversion, is called zero forcing in literature. There's one more thing called MMSC. Okay, I will tell you that when we do OFDM, I'll tell you how to do MMSC. For now, just, even zero forcing also will go into depth at that point. But for now, think of the zero forcing is nothing but if some channel is there in front of you, you just invert the channel blindly. That's called zero forcing. That's called, so this is called equalization. And this technique of equalization is called zero forcing. Okay, this is called channel equalization. Fine. Okay. So one thing is this. So this is a channel with a gain. Now this is a channel with a gain, ADB channel with a gain factor. Okay. So this channel with a gain factor can be thought of as a single tap channel. Okay? This channel can be thought as a single tap channel. Okay, why? What does that mean? What does it mean? What I mean by that? You have your baseband at your transmitter, and you have RF or something, and you have a gain to that. You transmit by an antenna. In the receiver, you have one more gain, GT, G receiver, followed by your baseband. Okay, so we can think of that there's a reflector, one reflector somewhere, and your signal is hitting this and coming here. There's only one tap. Okay, and the gain of this tap is some alpha. Okay, what did we put? Not alpha, no? Okay, so okay, so not alpha. I'll just make it beta. Just hold on. Call it beta. Okay, so your entire channel from baseband to baseband, from this point to this point, is nothing but beta times GT times GR. Okay, this is what we call as alpha. I will denote instead of alpha, I'll call this as H because it's easy. H is your channel number. Okay, I'll just call it H. Okay, H is defined as this. Okay, so effectively you have a single tap. So this also is going to be this path, because there's a path here. There's going to be a delay. There's going to be a delay tau 0. Okay, when whatever you transmit here, it takes some delay to reach the receiver, depending upon your distance and a lot of factors. Okay. But this beta may depend on the path loss, how it hits the walls and other things. But this is a single tap channel. Okay. So effectively, I can write, if x of t is the thing that's coming out of here, I can write, maybe we'll also assume GT and GR to be 1, just to make it simple. GT equal to GR to be equal to 1. It need not be, but it makes our life easy. Okay. So y of t is equal to h times x of t minus tau 0 plus thermal noise, of course, gets added here. Okay, thermal noise, n of t. Okay. So effectively, the single tap channel, what it's doing, it's giving you a gain. Gain means as a gain we have lost. That's what I mean. And it delays your signal by tau 0. Fine. Is this clear? This is a very simple model. This is what we were learning before.
Sir, can you again explain that h into t minus tau naught?
Okay, so x of t is so think of this. See, x of t is a signal that's coming out of your antenna. Let's assume it's a baseband signal. Okay, to keep things simple. Okay, so x of t is a signal that's coming out. Then what happens? By the time it reaches your receiver, it has a delay tau 0. It takes some time for propagation. Yes. Okay, because it has to travel this path. Maybe this path is 100 meters or so. Okay, So the time the receiver, what you get is a delayed version of whatever you transmitted. That is t minus tau 0, x of t minus tau 0. If tau 0 was, for example, this tau 0 was 100 nanoseconds, this will be t minus 100 nanoseconds. X of t, x is the signal that you're transmitting. X of t is the signal that you're transmitting. H is the channel gain.
Okay, this is x of t. I thought it is h multiplied with a t minus.
No, sorry. Maybe I'll put it big.
It is x of t. Okay. This is then.
Okay.
Yes.
So let's look at the channel response. Let's forget about noise for now. Let's look at the channel response. Okay. So I'll just forget about the noise first. Let's forget about the noise. Just let's look at only at the channel. Okay. So we look at the channel in the frequency domain. Okay, in the spectrum analyzer. So I take the Fourier transforms on both sides. I get y of f. H is a scalar, so nothing happens. If you take the Fourier transform of x of t minus t naught, what is the thing you get? You get x of f times e power minus j2 pi f times tau 0. Okay. So let's just recall what is the Fourier transform. I hope you remember what is the Fourier transform of a signal. This is the only time we require this. Don't worry. X of t is equal. So essentially, x of f is equal to integral of x of t e power minus j2 pi ft dt minus infinity. This is a Fourier transform. Most of you must have seen this. This is a Fourier transform signal. So when you delay a signal, essentially Fourier transform essentially the same as the original Fourier transform for x, but multiplied by a phasor e power minus j2 pi f0. Fine. Okay. This is just a digression. Okay. So now, what is the so is it chat? Beta b should be.
Are we assuming that the signal is aperiodic?
See, we'll assume that the signal has finite energy. That's sufficient. Okay. So if we assume that the signal has finite energy, then our finite power, then we are fine. Okay. We don't assume anything about periodicity in this thing at this moment. We don't require. Does that answer your question?
Sir, the Fourier transform has to be defined, right, sir?
So as long as, essentially it turns out as long as the energy in your signal is finite, then the Fourier transform is defined. So essentially, the Fourier transform to be defined, what you require is one of the conditions. This is the most stricter condition is this should be less than infinity. Okay.
Can it be considered as a band limited signal?
You can consider this as a band limited signal also.
Yes.
And another thing that we are doing
I think this is band limited signal only, and in the practical scenario also, we use the band limited signal. So.
Yes. So another thing is, one thing is you don't worry about the existence of Fourier transforms and other things. So what we can think of is you're taking some time window and it's band limited, so the energy will be finite. So the Fourier transforms and all this exist. Okay. What to answer is a very good question whether it exists or not, but let's not get into that. Let's assume it exists. It will exist. Okay. So what we have is we have y of f is equal to x of f into what? H into x of f into e power minus j2 pi f tau 0. Okay. So my channel, effective channel is defined as y of f by x of f. In this case, it will be, if you divide y of f by x of f, you get h times e power minus j2 pi f tau 0. Okay. What is the absolute value of h of f whole square?
And sir, what about the noise?
No, forget about the noise. When we're dealing with channel, we don't talk about noise. I'm just purely focusing on the channel for now. Okay. Noise will always be there. Okay, let's just focus only on the channel, so that the things, frequency, selectivity, and other things become clear. So when I do mod h of f square, h square mod times e power minus j2 pi f tau 0 whole square. So this will become mod h square. It's a scale. It's e power minus j2 pi mod square is always 1 into 1. So this is equal to mod h square. Okay. So essentially, when you have a single reflector, a single tap, your frequency response of your channel does not depend on the frequency. So if I plot it in the spectrum analyzer, if I plot it in the frequency domain, how will my channel look? my mod h of f whole square is a straight line. Okay, with gain mod h square. Okay, so this is called as frequency flat channel, or also called as single tap channel. Okay, so when you have a single tap channel, which is the case that we saw before, y is equal to hx plus n, what you have is, in the frequency domain, a channel response is flat. Essentially, there's equal gain across all the frequencies. Suppose your signal, maybe your signal, actual signal of interest will be this part. At that part also, everything is flat. The channel response is flat.
Can we say it LTI channel?
So this is an LTI channel, linear time invariant channel, because
same question I was asking day before yesterday. So if we model any channel, I think we should talk also about the what is in terms of LTI or non-LTI.
yes,
Thank you.
I'm going to tell you now. When we do the multi-part channel, it's an LTI channel again. That's more LTI. I'll tell you that. Okay. So now, if you look at this channel, we have y of t is equal. What did the channel? So finally, essentially, just to recall, we have y of n in the baseband domain is equal to h into x of n. That plus z of n. This is called a single tap channel. Okay, remember this. Okay. Now let's answer the next question. So until now, so essentially when we have y is equal to hx plus n, when we know h, we divide by h, and we are able to decode our data. Okay, this was case 1. Okay, now case 2, h is fixed but unknown. Okay, but unknown. You have y is equal to hx plus n model, but you don't know h. So what do you do? Okay, so this is where pilots come into picture. Okay, so what are pilots? Okay, so essentially, suppose I ask you this simple question. I ask you this simple question that I know my channel is y is equal to hx plus n. How do you find my h? I ask you this question. Forget about everything else. Okay, how do you do this?
By sending a known channel, by sending a known signal.
Yes.
And then
by sending a known signal. Exactly. That's absolutely right. So what we do is pilots are known symbols. When I say known symbols, they are known both at Tx and Rx. Okay. So beforehand, Tx and Rx decide on some pilots. They say that this is what you are going to transmit to me. Okay. So what happens? So if you think of your symbols being transmitted in discrete time, so each of this box is one symbol being transmitted. So you will transmit a pilot P1 here, P2 here, P3 here, P4 here, followed by data 1, data 2, data 3, data 4, data 5, so on and so forth. Okay. So what exactly is a pilot? So remember, we are always transmitting a constellation point. Okay. For example, if you are transmitting QPSK, I can say that P1, so this is symbol 0, this is symbol 1, symbol 2, symbol 3. Of course, data is random, so you don't know what symbol is being transmitted a priori. But pilots, I can say that I'll fix P1 will be equal to S0, P2 will be equal to S1, P3 equal to S3, and P4 is equal to S4. Okay, and I'll tell the receiver also, always the first 4 symbols in a frame or something will be pilots, and the pilots will always be S0, S1, S2, S2 and S3. I tell that a priori to the receiver also. Okay, so what is the first thing I'm going to send in the first frame? I'm going to send y is equal to h times P0 plus, and what noise gets added at that point. So y1 is equal to this one. First time instant, this is what is going to happen. Okay, maybe I'll put 0. Y0 is equal to 0 and 0. Okay, next time I'm going to send y1 is equal to h P1 plus, and I'm saying P1. This is what I'm going to receive. Y2 is equal to h P2 plus into. Y3 is equal to h P3 plus into. Okay, so I send the pilot. The receiver knows that the pilots are being sent now. So if the receiver obtains Y0, Y1, Y2, Y3, and it knows P0, P1, P2, P3, how does it find out H? Okay, so let's assume only the first equation. First, only one equation was sent. Let's assume all other equations are not there. Let's assume these are not there for now. Okay, let's assume first thing. So what will the receiver do? Can anyone tell me?
Divide the output by H.
H is not known.
Now divide the output by P0.
P0, absolutely. So what you divide is you have Y hat is equal to Y1, Y0 hat equal to Y0 by P0, which will give H plus N0 by P0. Okay. Similarly, you have Y1 hat will be equal to H plus N1 by P1. Similarly, Y3 hat will be equal to H plus N3 by P3. Okay, then what can the receiver do? No, receiver can say my estimate of the channel is equal to Y0 hat plus Y1 hat plus Y2 hat plus Y3 hat by 4. What will happen when I do this? All the 4 equations get added and divide by 4. So you'll get H back here plus N0 1 by 4 into N0 by P0 plus N1 by P1 plus up to N3 by P3. Okay, it turns out this also will be a native white. So this part is also a native white Gaussian. This also will be a Gaussian noise with lower variance. Because you are averaging it, right? When you average out, what happens? The noise gets averaged out faster than the signal. Okay, try to find out what is the power in this thing. Okay, compared to the power in this. Please do that as an exercise. It's actually very interesting to see. Okay, what is the power, noise power in this? So noise is uncorrelated. Remember, N0 square and N1 square are independent. Okay, what is the power in this versus what is the power in this? You will see that the power in this noise power decreases by a factor 4. Okay, so you get a better channel estimate. This is averaging. So this is how you find your channel. So essentially, what are done? Pilots are sent, and the pilots are known as the transmitter and the receiver. The receiver uses pilots to estimate the channel. Okay, so once the channel estimate is known, next what does it do? Next, how does it decode data? In the next cases, whatever some Y3 is done, so Y4 will be actual data, H times whatever data you want to send, X4 plus N4. Okay, some data we don't know, but H is known. Okay, so what you do, the receiver decodes the data as it says my estimate of my data will be equal to Y4 by whatever channel I have estimated. Okay, so there will be Hx4 by H hat plus N4 by H hat. Okay, if your channel estimate was correct, what will happen? This H by H hat will be very, very close to 1. Agreed?
Yes, perfectly right.
Okay, so this is what is called as channel equalization. Essentially, this is channel estimation. Using pilots, and this is channel equalization. Okay, in this case we are doing a simple zero forcing channel equalization. Okay, so for a single tap, this is very, very straightforward. Okay, I mean, you send pilots, you can automatically just divide by the pilots to get your channel, and then later at the later steps you divide by your channel to to get your data. Let's discuss a few points. Any questions or any discussion before we proceed? Okay, so it turns out a lot of the standard 5G standard is about defining these pilots properly. Okay, you will see that. Okay, so let's discuss a few points. The first thing is, we can immediately observe that the channel estimate becomes better and better as the number of pilots increase, because my averaging effect becomes, so 4 if I send 10, my averaging becomes better and the noise power goes down much lower. Okay, and I get better channel estimate. Okay, so first point is channel estimate improves with increasing number of pilots.
There is a need of optimization of overhead also, no?
Yes, that's what I'm trying to say. Okay, so but once you increase your pilot, but one thing you should realize is pilots do not have any information. Okay, they're just wasting. I mean, they're just used to estimate your channel, but I mean, pilots do not have information. No, pilots have no useful information. No useful information. Okay, so effectively you're wasting those. So for example, in this case, you are wasting this first four things. Sorry, this okay, this first four things you are wasting. Okay, you're wasting your channel 4 times. You're wasting your channel. Instead of sending data, you're sending pilots. It's a waste. Okay, but it turns out if you increase the number of pilots, your channel estimate becomes better. If your channel estimate becomes better, your decoding becomes better. Okay, so there's a trade-off between the number of pilots you send and your performance and your throughput that you get. You cannot add this thing in these 4 things are a waste of your throughput. Nah? So there's a sweet spot. It depending upon the particular thing you have, there's a trade-off and there's optimal number of pilots for each case. I mean, there's no universal rule for this, but each case you have to figure out what are the optimal number of pilots without wasting too many resources. How can you get the best performance? Okay, so this is what standard also tries to do. It tries to put as many number of pilots, but not too many, because too many pilots waste your resources and your spectral efficiency of the system goes down. Fine. Good. Any questions before we proceed?
It's all right.
Okay. Now, let's increase the complexity of the model. Let me introduce something called the multi-path model. Okay. So in the multi-path model, what happens is you have your antenna, you're transmitting your X of t. There are multiple reflectors, which is usually the case. There are a lot of reflectors in your rooms and outside, everywhere. Okay. What's going to happen? This waveform is going to hit here, come here. This is going to hit here, come here. Okay. So essentially what happened, each of them will have a different delays. This will have maybe tau 0 delay. It will have gain H0. This might have tau 1 delay, H1 gain. Tau 2, H2 gain. Okay. So effectively your Y of t would be H0, X of t minus tau 0. The same data is going. Remember this. Plus H1, X of t minus tau 1 plus H2, X of t minus tau 2. Okay, there's noise. I'm not writing the noise at this moment. For channel, I don't write the noise. Okay. So now you have, I'm just showing you 3 paths, but in general, you can have a lot of paths depending upon your environment and other things. Right? So if I now take my Y of f using the same principles like before, okay, it will be H0 X of f e power minus j2 pi f t0 plus H1 f tau. Okay, so what is my Y of f by X of f, which is equal to my channel? In this case, it will be H0 e power minus j2 pi f tau 0 plus H1 e power minus j2 pi f tau 1 plus H2 e power minus j2 pi f tau. Okay, so if it returns, now if you look at the absolute value of mod h of f square, okay, this is no longer flat. This is no longer flat. Okay, it will have some frequency response. It will have some frequency response. Okay, because it's no longer, I mean, see, if you take even the absolute value, it will depend on tau 0 h0, tau 1 h1, tau 2 h2. Okay, I'll show you a small
Time
example
delay.
in MATLAB. Yeah, it's called frequency selective channel. This is called frequency selective channel. Okay, so I'm going to show you a small example in MATLAB so that just it will become a little bit clear. I just wrote these equations. So it's nothing but I have some number of tabs. I put the delays. I put the delays in terms of nano. I said the first tab has 1 nanosecond delay. The second tab has 5 nanosecond delay, so on and so forth. Okay, and these are the channel path losses. Okay, I just plot first n equal to 1 tab 1. This is the first. This is a what is called frequency select. I mean frequency flat single tab. Sorry, one minute. Just hold on. You can see it's a flat channel. Okay, I mean, you see that across those channels flat. But now if I make the number of tabs to be 3, you can see there's a frequency selectivity now. So the channel response in the frequency domain has ups and downs. Also, you can see this is there is a 2. I can increase the sense. Okay. So when you have multi-path, you have frequency selectivity. Agree? Did you understand this?
Yes.
Sir, here I want to ask that initially you have started with n is equal to 1, number of step 1.
Yeah.
But we have got the various delay of 1, 5, 10, and 20. In one step, how can you have the variable time delay?
No. When I say N1, only the first part will be considered. Other parts will not be considered.
Okay.
So it will just read the first one. I'm not writing it every time. So I just, if I can put 4, it will take all the 4. Otherwise, if I put 1, it will take only the first one.
Okay.
Because the loop here, the for loop only goes from 1 to n. That's all. Okay, so if I put 4 tabs, it becomes more frequency selective. Fine. So what I want to emphasize is that as the tabs increase, depending upon the values of tau zeros and other things, the frequency selectivity is changed. For example, if I make the tau very small, for example, 0.1, 0.15, 0.2, 0.22, it becomes less frequency selective. Okay, so the delays and all these things play a very critical role in defining how your frequency selectivity of the channel is. Okay, that's what you should all remember. Okay, now let's get back to this thing. Okay, so any other questions before we proceed?
Sir, what would be impact of direct line of sight communication from y of t to x of t without any delay on the channel response?
So that's what this is the first channel that we saw. No? In the first channel that we saw, it's a direct line of sight. I mean, if you forget about the reflector, it's just one line. It will still be a single tap channel. Okay, I just showed a reflector. When I showed the reflector, you can think of there's a direct path also. Only one tap.
That will have minimum delay. That will have minimum delay. No,
Exactly. Absolutely right.
Krishna, that will have minimum delay. That's all.
Okay. But that is also single tap channel. Okay.
Excuse me, sir.
Miss Vijay, please.
Sir, actually, frequency selective fading means one particular frequency due to in phase or out of phase, the gain will be neutralized, sir.
Yes.
So how we can interpret here, sir?
So you can see that depending upon, so essentially what happens is the path lengths now in the frequency domain, the path lengths get converted into frequency. Okay. With different phasors. These are different phasors. No? E power minus j 2 pi f t0 is a different phasor from phi tau 1. So at some frequencies they get constructively added. At some frequencies they start getting destructively added. Yes.
That how can we visualize, sir, now with this 4?
So what I would suggest is, I would suggest you take only 2 taps. Okay, let's take only 2 taps. Okay, one tap is one tap. Let's assume it is 0 delay and gain 1. Okay, the other tap you just take tau delay and gain also you take 1. Okay, so then your effective channel in the frequency domain would be 1 plus e power minus j2 pi f tau. Yes.
Okay, sir.
You plot the absolute value square of this. Okay, if you plot the absolute value square of this will be 2 plus 2 cos theta, 2 cos 2 pi 4 pi ft, if I'm not mistaken. Just do this math. You can see that you will get channel like this.
Okay, got it.
Okay, so at some points it's just cancelling this one, the effect of this first part. At some points it's adding.
Thank you.
But in general, it will be more complicated thing. Okay, I mean some things you can do with math, something you just have to plot and see. Okay, so this is the channel part. Now let's come back to the receiver. That's more fun. So effectively, how do I write my discrete channel model? I'll write my discrete channel model, effective channel model, as I'll have sigma hi x of n minus maybe x. I'll just put different. Xk of n minus k plus z of n. K is equal to from 0 to capital L minus 1. Okay. So this is the multi-path. Can you please mute your mic if you're not speaking?
Mr. Manoranjan Srivasan, can you mute your mic?
It's called the multi-path baseband equation. Essentially, what is happening? Because of this multi-path and delays, your current symbol, your current output, not only depends on your present output. So if I expand this, let's expand this once for some L equal to 2 or something, L equal to 3, you get H0 x0 plus H1 x of n minus 1 plus H2 x of n minus 2 plus z of n. It depends on the delays of your multipath. Okay.
Sir, noise will also have the variable, na, that it should also have the k part.
No, what noise gets added.
Every part will have the different kind of that additive noises.
Okay, that's a very good point. But see, all the parts are superimposed at the antenna, and the noise gets added at the antenna.
Okay,
So
then
noise,
add how overall you are you're representing by with the
Z of n. So there's only one noise that's get added because noise is decorrelated across time.
Okay.
So Z of n will be the only one. That's an absolutely nice point. So now you see that your current output depends not only, sorry, this is X of n, sorry. Not only depends on the current input, but may also depend on the previous inputs with different channel gains. Yes? This is also coming in some sense, this is also called an ISI channel. Inter-symbol interference. You can think of this as inter-symbol interference. Okay, so you're having interference from your own transmitter, but for your previous symbols. Okay, so you see that immediately because of multipath, your channel become a little bit more complicated. Your receiver has to do something more. So you are interested in decoding X of n, X of n minus 1, X of n minus 2, and so on and so forth. But question is, now that you have an equation like this, how do you decode? How do you decode? How do you decode in frequency selective channels? Okay. How do you decode in frequency selective? Frequency flat, it was very obvious. It was very simple. How do you decode with this? Any thoughts? Okay. Okay, there's no, I mean, so if you don't have any comments, so essentially there are ways of decoding this. You use a class, I mean, you can use like what we did, single tap equalizer, there are multi-tap equalizers are there. Okay, we will not go into that because OFDM removes all this. It's called multi-tap equalizers. Okay, so multi-tap equalizers, what it does is it tries to invert the frequency selective channel. Okay? It's very, I mean, it's actually pretty complicated. What happens is the multipath effect increases as your bandwidth increases. You can see now you are able to see in the MATLAB. Now you can see as the multipath increases, as the bandwidth increases, you see more and more multipath. You see more paths getting resolved. Okay. So this kind of multi-tap equalizers become more and more complicated as bandwidth increases. It's actually really pain to actually build this multi-tap equalizers. For frequency selective channel. For 1 megahertz, 2 megahertz is easy. But when you go to 20 megahertz or 40 megahertz or 100 megahertz, it's actually extremely difficult to build these multi-tap equalizers that perform well. It becomes very they can be built. They're theoretically optimal also, but it becomes extremely complicated. Okay, it becomes extremely complicated and makes your system very what do you say, expensive in some sense. Okay, so this is one issue. So it's called multi-tap equalizers. Okay, so just remember. I mean, I'm not.
If Professor, if we use reverse channel matrix, so can we know the received signal in that case? If we calculate
if you use the what reverse signal matrix means?
Reverse channel matrix.
Reverse channel matrix. So effectively, it turns out to have invert matrices. Maybe I will. I'll give a small example in the homework where you can, for 2-tap channel, we can invert the matrix and check this out. Okay?
Right.
So even estimating the channel is a complicated.
For inversing also, you need to know that H0, H1, H2 at the transmission side so that we can, at the receiver end, we can inverse it.
Exactly.
Another problem over here.
Yeah, even to estimate the channel, now it's not so simple. Now, even if you send pilots, pilots also go interfere. Yes. Okay, this is called multi-tap. So this is a problem. See, I mean, in general, in digital communication class, we teach this for one semester, this multi-tap equalizers. I mean, it's a big part. But now, let you just have some faith in me, and when I say that they are complicated. I don't want to touch them generally unless it's absolutely necessary. There's one more point I want to highlight. I mean, when we in all of this. So when you have y is equal to hx plus noise. This was our model. Remember, it's x. We are transmitting x. Yes, we are transmitting x. This is our IQ. Okay, we are also essentially information is directly mapped to x. Yes, information is directly mapped to x, and x is what is transmitted. So essentially, this is called as it's a time domain. You're mapping the information to the time domain. Essentially, you're mapping information to time domain. Remember that. Yes, you're mapping information directly to time domain. The point becomes clear when I do the OFDM part. Okay. So essentially, you're mapping your information to a constellation which is in the time domain, and you're transmitting the constellation point itself into the air. And the receiver receives and processes. Okay, just remember this point. We'll come back to this in the next class again. Okay. Now I'm going to actually switch. Switch plates and ask a little bit of discussion. Okay. So suppose. So one of the things that we have in cellular systems, so we are talking about cellular systems here, okay, is we have to serve multiple users. We have to serve multiple users. Okay. So let us assume I am the base station and have user 1, user 2, user 3. Okay, this is my base station, user 1, user 2. Let's assume everything is single tap channel. Okay, let's assume that the channel from base station to U1, base station to U2, base station to U3 is a single tap channel. Let's assume. Okay. How do I serve these 3 users? How do I serve the 3 users? Tell me.
Using scheduling, sir.
Scheduling, exactly. But what way? What do you mean by scheduling?
Like sharing the channel resources in the time domain.
What? Okay, so you're sharing. What are you saying? So I will share. What you are saying is, Mr. Vijay is saying is, share the channel in time domain. Okay. So what he is saying is, you have a frame. Okay. Give the first maybe 4 to user 1. The next few things to user 2. And the remaining maybe to user 2. That's what you're saying. Yes? Mr. Vijay, am I right?
Yes, yes, sir.
Okay. This is called time division multiple access. Okay. Multiple access means essentially the same channel is being shared across multiple users. Okay. This is called TDMA. What's the other way of sharing? Can anyone tell me?
Frequency domain multiple access.
Then frequency
FDMA,
division
CDMA.
multiple access also.
Okay. So FDMA.
FDMA.
Okay.
FDMA.
So in FDMA, what do? You take your bandwidth, you split your bandwidth. You say that the first band of the bandwidth is U1, the second part of the bandwidth for user 2, and third part of the bandwidth is for user 3. Suppose you have 60 megahertz of bandwidth, you give 20 megahertz to one, 20 megahertz to one, 20 megahertz to other users. Okay. But now let us understand what are the issues in the time domain transmission with both FDMA and both TDMA. Okay, let's understand these issues. Okay, see, one thing is very sure that in cellular systems you have to use some multiple access because you want to serve more than one user. Okay, you have to serve you have to serve tens of users at each time instead. But that is certain that you have to serve multiple users. So whatever modulation scheme that you come up with has to be consistent. I mean, has to have ways of doing this. Okay, so first let's talk about TDMA. Okay, so TDMA, is there any problem with TDMA with when we have multipath?
Yes, sir.
Yes.
Interferences.
Yeah, what is going to happen? Base station is going to transmit U1, U2, U3. These previous symbols from here of the user 1 are going to affect the user 2 also. Okay, similarly, this one also will get effect. I mean, so sorry, this is the other way around. This will also affect this one, depending upon the number of multipath. So to avoid this, what people do, you can put a blank frame. You can put a blank frame, nah? There you don't transmit anything. Similarly, you put a blank frame here. You don't transmit anything. Okay, so this is some waste of resources. In the frequency domain,
Professor, that is rather, I could say that is the compensation of timing advance.
Its timing advance is in the uplink, sir. In the downlink itself also, you don't want between two frames between users to have interference among them.
Okay, only for the downlink.
So I'm just talking about the downlink. It's easier.
Right. Okay.
So in the FDMA, I just drew 3 lines, straight lines like this, saying that U1 will have this, U2 will have this, U3 will have this. But in reality, you can never have such sharp cutoff filters. No? In reality, you will never have filters that are like infinitely sharp. Okay?
Guard band.
So what are you going to do? You have to have a guard band. You will just, you'll have something like this. The second user will be like this. Third user will be like this, where you are wasting this resource. These frequencies are almost waste. Yes? Okay, so you have to have guard band in frequency. Okay. So there are 3 points. One is, first of all, TDMA, multiple access should, whatever scheme we come up with, multiple access should be easy. 2, simple multipath equalization. Okay, 3, have very good spectral efficiency. frequency selective channels. Okay, so it turns out OFDM is a solution for all this. Okay, it turns out, I mean, of course, it has other problems. I'll come to the problems when I'm teaching OFDM, but for now, we'll make OFDM the hero. It says that OFDM makes multiple access absolutely easy. Okay, it's a beauty. Okay, and the multi-path equalization, essentially, what OFDM does is OFDM converts a frequency selective channel into multiple single tap channels. Okay, it takes a frequency selective multi-path channel and converts it into few thousands of single tap channels. Okay, and it turns out the OFDM is also capacity optimal in terms of when you have frequency selective channels. A particular version of OFDM is capacity optimal when you have frequency selective channels. Okay, so with this basic background, we can go into OFDM. So in the next class onwards, I'm going to start OFDM. Okay, I'm going to start teaching about frequency time grids. We will introduce. I'll introduce OFDM in the next class, and from the next 3-4 classes, we'll finish. We will go through pilots in OFDM. How do you do equalization? How does multipath get converted into single tap in OFDM? What is meant by cyclic prefix? Okay, we are going to go to all the points. What is subcarrier spacing? We'll go to all the points carefully. And we're also going to understand what are the drawbacks of OFDM also. Okay, that's also very important in designing the system. Okay, so this is the basic background we require to at least understand why OFDM is important. Okay, so today what did we learn? We learned single tap. In single tap, equalization is easy because you can send pilots, and we also learn the notion of pilots. Single tap equalization and channel estimation are easy. Multipath results in frequency selective channels. And I mean, I made a statement that frequency selective channels are generally difficult to do time domain equalization. Essentially, when you transmit data in the time domain, it's very difficult to do equalization. Okay. And one of the other things that we require in cellular systems are multiple access, because we want to serve multiple users. Okay, we know of two things. One is called TDMA, one is FDMA. There's another thing, CDMA, but anyway, that's not of concern right now. So, but TDMA and FDMA have some inherent problems with respect to efficiency, because you have to either put guard bands in time and in frequency, which will result in loss of efficiency. Okay. So in the next class, we'll look at OFDM, which provides a nice solution for these three problems. Okay. And from there, we'll take on to the 5G standard very soon. So thanks everyone. So today I'm going to upload also some one basic basic homework. One is the MATLAB and other is the normal written homework. Okay, but I'm going to make it easy this time. For the first two homeworks, I'm going to keep it relatively easy and intuitive. We will just so that all of you can participate and finish up those problems. Any issue, please let me know. By today evening, I will send you the MATLAB instructions. Okay, I'm working with MathWorks for this, and I think it should be done by today evening. Okay, so thank you everyone.
Thank you, sir. Thank you.
Thank you. Very nice.